Thank you. So welcome to the second talk of Bezrukavnikov's equivalence, and we will be mainly following Bezrukavnikov's original paper, and I hope my talk will be serving as a reader's guide to his original paper. So let me first briefly recall all the notations on the automorphic side. Bezrukavnikov's original paper worked in the equal characteristic situation, though the new development in this area possibly makes it work also in mixed characteristic, but I will work in the equal characteristic situation. So K equals K bar is a algebraically closed field of characteristic P, and F is thisLohon series ring, contains the ring of integers, which are denoted by O. Okay, so G is a speed reductive group over F. And then you can convert it into an object which lives over K by taking the loop group. And I need to fix a hyperspectral O model of this group G. But since I'm in the equal characteristic situation, for notational simplicity, I may just assume that my group G is defined over K. So I choose a barrier B inside G. Then this gives me an Iwahori subgroup I, which is the pullback under the evaluation map from the arc group to G of the barrier. This is the Iwahori subgroup. And it has the so-called pro-unipotent radical, which is just the pullback of the unipotent radical of B. And on the automorphic side, the category that we are interested in are this so-called unipotent monodromic affine Hecke category and their variants. This is the automorphic category. So you may also write this double quotient as a fiber product of classifying stacks. And this gives you a convolution monoidal structure. Okay, that's the automorphic side of Bezrukavnikov's equivalence. And on the spectral side, oh, by the way, my sheaf theory are all erratic sheaves, so today I'm only going to work in the characteristic zero situation. That's the setup of Bezrukavnikov's original paper. On the spectral side, I have G hat, that's the Langlands dual group, over lambda, which is Q bar. And it comes with a canonical pinning, which means it contains a canonical Borel subgroup, a torus inside the Borel subgroup, and the trivialization of all root subgroups. So the spectral side of Bezrukavnikov's equivalence, the spectral category, is what's called incoherent sheaves on the so-called Steinberg stacks. And its variants. So what is this formal completion? So you have a natural map from B hat to T hat, which induces a map from this quotient to the adjoint quotient t hat mod t hat, but the t hat conjugation action on itself is trivial, and you have a natural map further maps to t. So this formal completion means formally completed along the inverse image of 1 inside t hat. Right, and also as a fiber product, the standard convolution pattern also endows this category with a convolution monoidal structure. Okay. The original paper, the original theorem of Bezrukavnikov basically states the following. So there are equivalences of categories. Sometimes it's also called a constructible coherent equivalence because it links some sheaf of constructible sheaves with some sheaf of coherent sheaves. So as I said before, there are certain variants of both the automorphic category and the spectral categories. They all fit into certain equivalences. So you may notice the pattern that if I replace I plus by I, then on the spectral side, I replace this formal completion of B mod B by U mod B. So you may guess that if I consider sheaves on LG double quotient by I, then it should correspond to incoherent sheaves on this fiber product. But for technical reason, on the automorphic side, I need to do some small modification, so it should be replaced by what's called int sheaf FG. Or if you don't want to change the if you don't want to change the automorphic side, then you need to do some modification on the spectral side. So you can add what's called the nilpotent singular support condition. But I will not talk much about it today. Furthermore, as I said, the categories in 1 and 3 have both sides are actually monoidal categories, and so you can actually build a monoidal equivalences in these two cases. And 2 will be a bimodule over 1 and 3.
Is 3 prime also?
Yes. Okay, any question about the statement of the theorem?
Is it too late to ask the following very basic question? Why are the objects on the right the correct automorphic categories?
Well, they are categorification of the affine Hecke algebra. So
Can you repeat the question?
the question is why on the automorphic side we consider these categories, and
On the right side.
oh,
Spectral
on the spectral side. So I guess one reason was explained yesterday in David's talk. And so there's this theorem of Cartan-Lustig, which gives a k-theoretic realization of the affine Hecke algebra in terms of some spectral data. This is morally just the coherent sheaves on that stack, while Cartan-Lustig's theorem deals with k-theory of that stack. So it's a natural categorification of the theorem of Cartan-Lustig.
Is finitely generated like constructible plus
Yeah, it's what some people call constructible.
what's the difference with
I mean, I think in this language of, so by sheaf I mean this co-sheaves that was introduced in Mingjia's talk, and this one was not introduced, but so Bezrukavnikov's paper originally, well, he didn't discuss much about sheaf theory, but what he used is actually this. But from this, it's not too hard to get this 3 prime.
I think it just states something about small categories, so I think it's just like
Yeah, so what he said is like sheaves here is current to coherent sheaves here. Right, okay, so so I will mainly focus on 2 today, and that's also what Bezrukavnikov did in his paper. Because it's technically easier, so if I denote this as T prime, this fiber product, then I can actually remove this formal completion because the right factor here is precisely the preimage of 1. So it's something more easier to study. And the strategy is as follows. We first build a functor f from imperfect complexes on this ST prime to this category, this automorphic category, which I denote by H prime. You may think of this as the spectral action in this context. Then I pass to the right adjoint to get a functor from the automorphic side to the spectral side. Well, since these are inside so-called PRL, they automatically has right adjoint. And thirdly, Bezrukavnikov proved that when you restrict to compact object here, they are precisely constructible sheaves here. Then this functor FR factor through coherent sheaves inside imperfect complexes. So I denote this induced functor by the Cyrillic letter B. And if I take the incompletion of that, which I denote by the capital Cyrillic letter B, then it's what we expect to be an equivalence. It's the Cyrillic letter. Right, so that's the plan, and I don't think I have time to discuss a lot about the proof, but I will try to recall some ingredients into the proof. Okay, so let's first focus on the automorphic side. Then, as we know, this category, this affine Hecke category, categorifies what's called affine Hecke algebra. And inside this affine Hecke algebra, there's a translation part corresponding to the co-character lattice of T, which you may think of as K0 of the category of representation of T hat. So the categorification of this translation part is precisely the what's so-called Wakimoto sheaves, which was denoted by J yesterday. So it's a functor from rep T hat to the affine Hecke category. And furthermore, inside here, I have the center of the affine Hecke category, which by a theorem of Bernstein is isomorphic to the W finite invariant part in this translation part. So W finite is the finite Weyl group, and it acts naturally on the co-character lattice. Then by this so-called Satake isomorphism, you may view this as K0 of representations of G hat of the dual group. So a natural categorification of the central part would be a functor, which I denote by Z, from rep G hat to the affine Hecke category. And I will briefly recall the construction of this functor, which is called Gates-Gray's central functor. Right, or maybe before I introduce its construction, I may list a bunch of properties of this functor. First, it's monoidal, because we expect that it to categorify inclusion of algebra. And it is central. What do I mean by central? Precisely in this content, it means that this monoidal functor factors through what's called E1 center of the target. So this Z is the E1 center, which is not the same as Bernstein center used in other talk, but it's rather in the sense of Jacob-Lurie. And the E1 center always has a natural structure of an E2 category, and this functor is actually E2. Or I should not say is E2, it has a natural E2 enhancement. Okay, so, well, concretely,
I have no idea what E1 or E2 mean. Can you say like 2 sentences?
E1 is just a monoidal, and E2 by down additivity is E1 in E1.
That doesn't help.
We don't actually need the E2-ness, here, but we do need the fact that it factors through the E1 center, but it can be understood.
So it's monoidal plus a little more. Is that a human way to think about it?
The EN are various infinity categorical notions of commutativity. I guess that's where they get that.
I've heard this slogan. But okay, sorry.
Yeah, so concretely what it means like for any representation G hat and for any sheaf on the Hecke stack, there's a natural isomorphism of these two convolutions, which you, but I mean, plus so-called higher coherences, but it's an infinitely amount of data. So the more precise way to say it is to use this language of E1 center and E2. Okay, so we briefly recall the construction of this functor. So it's constructed using some non-constant global group scheme over A1. Or if you want to work in the mixed characteristic, maybe it's like you should modify it in some VStack language. So I denote by curly G to A1. I will not explain the construction of this non-constant group, but it satisfies the following property. So when you restrict it to spec O, it's isomorphic to this Iwahori O model of the group G. And when you restrict to Gm, it's isomorphic to the constant group G times Gn. Or G is this thing defined over K. Yeah, you think of it as the origin.
The origin or like the complete local range of origin?
I really take spectrum of O, I think. Yeah. That's in the algebraic geometry setting. O is a ring of integers inside F. So it's a K double. Sorry, what? No, sorry, A1 is over K.
So A1 is globalizing O.
Yeah, yeah.
It's the completion of the origin.
Completed local range of the origin.
Yes,
Okay.
yes. Right, so then I can consider the global Hecke stack, which I denote by Hecke globe. It's something also over A1 or K. So it parameterizes the following moduli problem. So I consider two G. First X is a point on A1, and E1, E2 are G torses, where I restrict it to the complete local ring at this point X. Well, I think what I'm describing here is really just the K point of this moduli problem, but you can easily modify it to be functorial. And this phi is an isomorphism of these two G torses on the punctured disk around X. So then you can see that, say, the special fiber of this global Hecke stack is precisely the Hecke stack at the Iwahori level that we studied before. And the restriction of this global Hecke stack over Gm is the hyperspecial Hecke stack times Gm. So now the definition of this functor Z from rep G hat to the affine Hecke category is given by following. It's given by taking a nearby cycle. So for any representation V, first by this geometric Satake isomorphism, I can regard it as a perverse sheaf on this hyperspecial Hecke stack. Then I tensor it with the constant sheaf on Gm, and I take nearby cycle.
So what is dx? Just A1 minus X?
Dx is like is the complete local ring at X. Yeah, so if you choose a coordinate at X, it's just a spectrum of K double bracket Tx, where Tx is a coordinate at X.
So E1, E2 are not defined in the...
So in the categorical situation, there are always extra data. You cannot say a functor is U1, but you need to provide enhancement. And what I describe here is does not include such enhancement.
So E1, E2 I meant for the
Oh, sorry.
So they are only defined on this.
Yeah, they are only defined on this.
So you have global because you also parameterize the point, or why is it called global?
It lives over A1, and actually you can replace A1 by any smooth proper algebraic curve or not proper. Yeah, that's why it's sometimes called global. Right. Okay, so some basic properties of this functor Z. So that V is filtered by the central sheaf that was introduced yesterday. By Wakimoto sheaves that was introduced yesterday. And this just categorifies the fact that the center is a subalgebra inside the translation part.
So what is psi?
Psi is nearby cycle. Okay, and furthermore, if you take V to be V lambda, that's the highest weight representation of G hat of highest weight lambda, then there is actually a natural map, which I denote by B lambda, to J lambda, which corresponds to taking the top of the Wakimoto filtration. And on the spectral side, morally, this corresponds to the fact that in rep B hat, as representation of the Borel, you have a natural map from V lambda to the character lambda. And this data actually needed later in our construction of spectral action in this context. Okay, any question about the central sheaves? Okay, so now we have enough data to construct the spectral action. So we start from just the representations of G and T. On the G part, we can take the central sheaf, and on the T part, we can take the Wakimoto sheaves. So this gives me a functor from representations of G and T to the affine Hecke category. And if you want to be careful why this functor is still monoidal, it's precisely because of the fact that Z factors through the E1 center of the target. Otherwise, if you take tensor product of two monoidal functors, they will not be monoidal in general. Okay, and I would like to extend this functor to a functor from point mode B hat. And how do I do that? Notice that this, maybe it's better to write this as point mode B hat. Then you can notice that I can also present it as G mod U, mod G mod T. This is what I want to extend. And this functor geometrically, so if you ignore the stacky part, it's just a pullback from a point to this space G mod U, which is sometimes called the quasi-affine space in representation theory. And its structure sheaf is very rarely understood, and this is what's called a monadic situation. Monadic is pullback. Degenerate everything here, especially in characteristic zero. And right, so I think but I'm happy to discuss more in Q&A, but I don't want to say much about category theory now, but there's a quite general formalism and applying that. So general formalism. Plus the data of this B lambda that I just introduced before will provide such an extension.
And this is still monoidal.
Yeah, and it is still monoidal. Okay, so we are getting closer to our target, but not quite, because what we want is something like B mod B, not point mod B. But after attending 3 lectures on categorical traces, you must have noticed that this thing is precisely the loop space of point mod B hat, and this category is the categorical trace of the previous category. But it's not quite, because it's in the category of commutative algebra, not just as monoidal category. But modulo that subtlety, my content is the data of such extension should correspond to some monodromy automorphism along S1. So this thing can be understood as, let me introduce another notation. Something like maps from S1 to point mod B hat. Then the data of such extension should correspond to some monodromy automorphism along S1. But we do have such data because recall our construction of the central sheaf used on nearby cycle, and nearby cycle comes with a natural monodromy automorphism. So this finishes our construction of a functor from, okay, so summary. I can construct a functor from in the path of B mod B to the affine Hecke category. And there's a similar construction in the monodromic situation.
So in the previous step, when you were extending, you said it's by general formalism. Could you repeat what the general formalism is?
I don't want to discuss it now, but if you still want to ask, we can discuss in the Q&A section. Moreover, in this case, what some people call unipotent case, it actually factors through U mod B. And in the second situation, it factors through, well, okay, here I have to use int co because I'm working on some formal scheme. Right, so now we have okay, so we have a map from this tensor product to endomorphism of H prime, where H prime is the automorphic Hecke category that was in the second situation. So it's sheaves on I plus mod LG mod I. How do I do that? So for the first factor, I first map it to this unipotent, to this equivalent version of Hecke stack. Okay, I probably change the order. Okay, so the second factor maps to the unipotent equivalent version of the Hecke stack, and it acts by right convolution on this category. And the left factor maps to the monodromic affine Hecke category, which acts on this category H prime by left convolution. Furthermore, we know that these central sheaves are central, which in this context means that it actually factors through this relative tensor product over G hat mod G hat, where on this G hat part, this action is given by central, the convolution with a central sheaf, but as I explained, convolution with a central sheaf on the left is the same as convolution with a central sheaf on the right. So you have such, okay, we have constructed such an functor, and by something mentioned also in Arnold's lecture, there's a relative coolness formula in this characteristic zero situation due to Benzui, Francis, and Adler. So here it's quite important that the characteristic of lambda is 0. Okay, in this situation, we have a relative tensor product, a relative coolness formula. And this is exactly the stack ST prime that I was studying. Okay, so let me summary what we have done. We have really constructed a spectral action. In this case, it's really an action on this H prime affine Hecke category. But what we really want is a functor from the left to the affine Hecke category. So from an action to a functor, we just need to evaluate this action on certain object inside here, which is usually denoted by psi called big tilting sheaf or anti-spherical projector. And so by evaluating at this object, I get the desired functor, which is the f that I described in the plan. So now let me briefly recall the construction of this big tilting object.
Sorry, the monadal structure on inverse ST prime?
It's tensor product. So it's not, up to now, I have said nothing about the convolution monoidal structure. Okay, if you want to be more careful.
Is like not very symmetric, right? There's not even a convolution.
Yeah, but even if you do the construction in the other two situations, you still use the tensor product instead of convolution. Okay, so let me recall the construction of this big tilting sheaf. Yeah, this is a very good example that I. No, it's still not convolution. It's always this tensor product, actually. So what you get is not the desired monoidal structure that we want. Yeah. Right. Okay, so this is a perfect example that I sometimes try to convince people that category theory is easier than functional analysis. So let's fix a non-degenerate additive character of I minus, which is the pro-unipotent radical of the opposite Iwahori subgroup. Then we have this average functor, or some kind of Whittaker average, which goes from the affine Hecke category to the space, well, it's called Whittaker category, which is just the categorification of the space of Whittaker functionals. But yeah, so far it's not so different from what people usually do in, say, harmonic analysis. But what's
I plus is like really IU, right?
Yeah. So the advantage of category theory is that I can take a right adjoint to this functor, while in the situation of functional analysis, I'm not aware of such an operation. And so I can define, well, this object is usually defined by this applying this functor and applying this right adjoint again to this unit object that was denoted by delta 1 yesterday in Dongru's lecture. And yeah, this is a definition, and if you want to be more careful, this functor psi, or this object, actually depends on my choice of a Whittaker datum on this Whittaker character psi. So if I want to be more careful, I add a psi here. But this is then consistent with all other phenomena in local Langlands where you need to rigidify your equivalence by some Whittaker datum. Okay, so I have introduced my, I think I finished my introduction to this construction of the functor f. Are there any questions? Are there any questions?
Why the average functor is
Oh, it's. I did not. The question is, what is this average functor, or why does it exist? And I did not define this average functor at all. But if you are familiar with the parallel theory, just for affine Hecke algebra and Whittaker functions, then you should not. You should be able to figure out the definition. For my content is the definition is exactly the same as the one that you do at the function level, but then we can take right adjoint, which is something that does not exist at the function level. Any other question?
You say evaluate on XC, you really mean like act on
Yeah.
XC, right?
Yeah, so more precisely, I have constructed a functor, a monoidal functor to this category of endomorphism of H,
Right.
H prime. Then I can evaluate at this object. Right, so just a second. And okay, I have constructed this functor f. Sorry, it's from the spectral side. Then I can take the right adjoint. So now it comes to the part what's called functional analysis in Bezrukavnikov's paper. So we want to characterize some coherent sheaves on X inside int_perf X. This part is called functional analysis in his paper. Okay, so we are in a very general situation. Say X is of the form Z mod H, where Z is a quasi-projective scheme over lambda. That is some algebraically closed field of characteristic 0. And H is a reductive group over lambda. Then Bezrukavnikov proved the following quite formal statement about characterizing Koch X inside int_perf X. So suppose you have a functor f from int_perf X to a category C, which is, as always, in PRL and compactly generated. Then we can pass to the right adjoint FR from C to int_perf X. Let's assume the following. No, I mean this category C is compactly generated. So let's assume that F is fully faithful. And let's assume that the restriction of the right adjoint of F to the subcategory of compact object factored through Koch X. then let me denote this capital psi by the restriction of FR to the subcategory of compact objects. Okay, so we assume further that this subcategory of compact object in C has a bounded T structure. By the way, you should always consider the C to be the affine category in mind. And we can consider the following three properties. The first is that this functor psi is of bounded amplitude. Which means that there exists some large integer d such that psi maps the say connective part to something in co less than or equal to d, and maps the co-connective part to something that's co greater than or equal to minus d. Yes. This was denoted by A, this is denoted by B in his paper. So the second condition is assume there exists some D such that for any sheaf F, sorry, not sheaf, any object F in this C omega, if psi F is connective, then F is not far from being connective. And the property C is that if there exists D such that for F, a compact object in C, you have the following implication. So if the cohomology of psi F is 0 when I lies in this range, this property implies that the zeroth cohomology of F with respect to this T structure on C omega is 0. So these three are all quite formal properties, but by some very clever functional analysis style arguments, Bezrukavnikov proved the following. So if this functor F satisfies condition B, then this psi is automatically fully phaseful. And if it satisfies both A and C, then this psi is an equivalence. No. Right, so then our goal is to apply this quite general formalism to our situation. And so again, it's a combination of some soft analysis and some real input. So I think I will not recall all the soft analysis part, but probably let me just say one non-trivial geometric input is the following. Yeah. So there's a theory of Lustig's A function. Which tells you that when you convolve to object, right? So of course, in our application, we endow this CW category of constructible sheaves with the perverse T structure. So we would like to analyze the Bezrukavnikov called almost the exactness of this functor. And on the automorphic side, one key input is the following: when you convolve two objects, two perverse sheaves, and in this, so in the hyperspectral level, the famous geometric Satake equivalence tells you that the convolution is again a perverse sheaf, but in the Iwahori level, it's no longer the case. Nevertheless, this Lustig's theory of A function tells you that the result of a convolution still has some explicitly bounded perverse amplitude. So it's bounded in this range. And this actual number is not important for the functional analysis part, but Lustig actually proved this. Okay, I think that's what I want to say about the proof, and maybe let me say some compatibilities and other stuff. So any question about the proof? Okay, so first, as already noticed by Arnold, my construction does not take care of the convolution monoidal structure. So we do prove some equivalence of a category, but in the categorical situation, you cannot say an equivalence is monoidal. Rather, you need to provide all other data to give rise to the monoidal structure. And in the one categorical setting, this was done in section 10 in Bezrukavnikov's original paper. But it seems hard to enhance that to an infinite categorical monoidal structure. And in the Betty setting, this is recently done in a paper of Gabriel Dillon and Jeremy Taylor. But unfortunately, they are in the Betty setting. Also, this Bezrukavnikov's equivalence satisfy the following compatibilities. So first, on the automorphic side, if I fix FQ rational structures, then I have a relative Frobenius action. I want to be more careful, put a twist 1 here. And this operation corresponds to something very natural on the spectral side. I denote this by Q upper star, where Q is this operation that's induced by raising every element to the Q's power. Or if you want to work in the Lie algebra setting, that's just a multiplication by Q. So there is such a commutative diagram. The second compatibility is the compatibility with respect to outer automorphisms. So remember, we picked a Whittaker datum. Psi, which induces a pinning on the spectral side. And there's a canonical isomorphism of pinged automorphism on both sides. So if I have an pinged automorphism gamma on the automorphic side, it naturally corresponds to something gamma hat on the spectral side. And I claim that for Bezrukavnikov's equivalence, I have the following compatibility with outer automorphisms. So on the spectral, on the automorphic side, I consider pullback by this automorphism gamma. Then on the spectral side, this should correspond to push forward of this gamma hat. Actually, if you want to be more careful, say, if I denote this equivalence by psi, where psi indicates the choice of this big tilting element, then what you naturally get here is this equivalence associated to the gamma pullback of psi. But since gamma is a pinged automorphism, this additive character equals psi here. So you can do slightly more general if your gamma is not assumed to be a pinged automorphism, but just fixed G and B. Then what you should put here is this equivalence associated to this additive character. The third one is compatibility with respect to Verdier duality and Grothendieck-Serre duality. So for this, since I work with duality, it's better to restrict to subcategory of compact objects, where this notion of Verdier duality really coincides to what people usually call Verdier duality. So you may naively just expect that the Verdier duality on the automorphic side corresponds to the Grothendieck-Serre duality on the spectral side. But it's not quite the case, but you need some small twist. So on the automorphic side, this Verdier duality should be twisted by convolve delta W0 on the right and convolve nebula W0 on the right, on the left, where W0 is the longest element in the finite well group. And this nabla and deltas are the standard and co-standard sheaves introduced yesterday. On the spectral side, this you may expect that it corresponds to Grothendieck-Serre duality, but you also need to twist it by theta push forward, where this theta is something called Cardan evolution. And also, in the second equivalence, I need to use minus psi, this additive character. Okay, so similar compatibilities also work in the cases 1, 3, and 3 prime in the original setup. Moreover, in those cases, they actually have natural monoidal enhancement. So these diagrams are not just commutative diagram of functors, but commutative diagrams of monoidal functors between monoidal categories. And
So can I be picky about something?
yes.
I kind of think we should call it the Chevrolet evolution and the Hecke evolution.
Okay, I had Chevrolet here. Thank you. So, yeah, so the proof of this compatibilities are not very hard in general. Maybe the hardest one is the third one, where it looks more complicated. And so for proof of the third compatibility, basically you trace all the construction of the spectral action and you check compatibility at every step, but one important input is to show that there's a canonical equivalence when you evaluate it on the tilting object, on the big tilting object. And for this, it's better to use another construction of the tilting object. So there is certain nearby cycle construction of the big tilting object. And then you use Garber's theorem that nearby cycle commutes with duality. I think I'll stop here. Thank you.